Hello everyone, my name is Shengshi Dong. I'm from Nanjing University, China. It's my honor to take part in great project in the real laboratory of EMPC from October 8, 2016 to January 26, 2017, and my supervisors are Professor Amin Tan and Jean-Michel Pierre. My major work during my segment is to find the small mechanical behavior of energy diaphragm wall using physical and mechanical modeling. My outline is about 5 parts: introduction, physical model, numerical model, result, and conclusion. First, I should introduce what my work focuses on. A small active or energy geostructure is a system that consists of conventional geostructures and individual or several pipe circuits in order to enable heating exchange with the surrounding ground. However, most of the existing studies was related to the small mechanical behavior of amplifiers. Besides, field data on the small mechanical performance of energy diaphragm walls have been published. So, during the segment in EMPC, we presented a study to evaluate the small mechanical response of energy diaphragm wall by using physical and numerical modeling. As shown in this figure is schematic view of the experimental setup. A small-scale concrete diaphragm wall was installed inside the metal cubic box. The internal height and the width of the box are similar to those of the wall. The thickness of the box is 25 millimeters. That is high enough to consider that the box is indefinable in its experiment. The model box was exposed in the indoor air, and the heat convection between the surface and the air is natural convection. The box was filled with dry sand, compacted at a density of 1.62 milligram per cubic meter. The temperature in the soil was measured at various locations situated at 1 meter depth. At this depth, the temperature sensors were distributed in 3 lines, 2 on the left side and 1 on the hand side. That allows measuring the soil temperature at different distances from the diaphragm wall surface at the same depth. The diaphragm wall was equipped with high-density polyethylene pipes for heating purpose, and also various sensors to measure earth pressure, temperature, and strain. The pipes were distributed on a plane located at 0.055 meter from the left-hand side surface of the wall, and the distance between the pipes was 0.17 meter. This figure is the details of the pipes and the diameters arrangement. Several diameters were tied to rebars to measure the strain at the various locations inside the wall. After the installation of the experiment setup, heating was applied to the wall in order to study its small mechanical behavior. For that, water having a temperature of 50 degrees was circulated inside the pipe with a flow rate of 0.03 cubic meter per hour during 75 hours. Besides the temperature evolution, which was measured at various locations inside the wall and soil, as pressure at the soil wall interface and strains inside the wall were also recorded. In order to predict the mechanical behavior of the wall during this experiment, the finite element method using answers was used. This figure shows the 2D mesh. Plane strain conditions were applied corresponding to the boundary conditions of the experiment. Heat flux was supposed to be negligible at the boundaries of the mesh. The horizontal displacement at the left-hand side and the right-hand side was restrained. The vertical displacement at the bottom of the mesh was also restrained, while the stress applied to the top of the mesh was none. The constitutive laws used in this study are summarized as follows. First, only conduction is considered for heat transfer. Second, the mechanical behavior of the wall is linear elastic, while that of the soil is elastoplastic, with drunk Prague yield criterion. Third, the small mechanical behavior of wall and the soil is linear elastic. In order to simulate In order to simulate the heat phase performed in the experiment, the temperature of the pipes was imposed. The initial temperature of the whole system was first fixed at 10 degrees. To start the heating phase, the temperature of the pipes was increased from 10 degrees to 48.5 degrees in curve during the first 20 hours. Afterwards, it was maintained constant until the end of the experiment. This choice allows fitting the prediction to the experimental data of the temperature measured by the sensor that is closest to the pipes. This figure shows the result of temperature variation between experiment and the numerical simulation. It shows a good agreement with the experimental results that confirms first, in this experiment, the heat transfer is mainly governed by the heat conduction, and the small boundary conditions used in this simulation are acceptable. Second, heating induced quick increase of the temperature at the location close to the pipe, while the temperature at the location far from the pipe increased more slowly. This figure shows vertical strain and stress versus elapsed time at the various steps on the left-hand side and on the right-hand side. The results show similar trend for all these sensors. A quick increase of strain during the first 20 hours, followed by a stabilization phase. The final strain is in the range of 50 to 70 microstrain, but the numerical results on the vertical strain and the vertical stress show differences between left side and right side. These differences can be directly linked to the heterogeneity of temperature distribution of the wall. This figure shows stress versus elapsed time at various steps on the left-hand side and on the right-hand side. For the left-hand side, the variation of earth pressure is more significant at higher depths. For the right-hand side, the general trend observed is different. At a 0.33 meter depth, the two earth pressure sensors show quick increase with the heating, and the final average value equals 6 kilopascal, which is higher than other depths. The numerical results corresponding the sensors 1 meter and 1.67 meters depth show good agreement with the experimental ones for both sides. Even the decrease of the express cell at 1 meter depth on the right-hand side was well predicted. However, the numerical results corresponding to lower depths are slightly different from the experimental one. On the left-hand side, the numerical simulation shows a decrease of earth pressure during the first hour, which was not observed in the experiment. On the right-hand side, the final value of earth pressure increase equals 12 kilopascal, while the experimental one equals 6 kilopascal. These problems would be explained by the weakness of the used constitutive law when predicting the behavior at low stress levels. In order to better understand the results on the change of earth pressure, the deformed mesh of the experiment is shown in this figure. Heating induces first small dilation of the wall that tends to increase the earth pressure at the soil wall interface. However, as the pipes were located closer to the left-hand side, the temperature distribution is heterogeneous. As a result, the temperature on the left-hand side increases more quickly than that on the right-hand side. That induces then a bending of the wall that can be seen clearly on this figure. This bending contributes also to the modification of the earth pressure. Besides the increase of earth pressure related to the wall dilation, the wall bending decreases the earth pressure on the left-hand side and increases that on the right-hand side. That explains why the increase of the earth pressure at 0.33 meter depth on the right-hand side is higher than those at higher depths, and the order is opposite on the left-hand side. In addition, the bending of the wall also explains the decrease of earth pressure observed at 1 meter depth on the right-hand side during the first few hours. Through using both physical and numerical models to study the small mechanical behavior of the angular diaphragm wall, the following conclusions can be drawn. First, heating induces small dilation of the wall. The vertical small dilation mobilizes the shaft friction between the soil and the wall and then modify the axial stress inside the wall. The horizontal dilation increases the earth pressure applied to the soil wall interface. Second, as the pipe layout was not symmetric, the small dilation bends the wall, resulting in different stress strain response between the two sides. Third, the numerical model using an elastic law for the small mechanical behavior of soil is sufficient to predict the behavior of the wall under small loading. Fourth, in spite of the temperature difference between the outlet and the inlet fluid temperature that induced a heterogeneous temperature distribution inside the wall, a 2D numerical model is sufficient to predict the main feature in its small mechanical behavior. That's all. Thanks for your attention.